All right. Yeah, thank you very much for having me here, I guess. I'm E from CMU, and I'll be talking a bit about our work on towards more stable proofs for SMT-based verification. So this presentation will draw materials from the following papers, and obviously I didn't do all these work by myself. So let me first start very briefly with some backgrounds on SMT-based verification pipeline. We start with the source code, then we have the verification framework, which includes Dafny, for example. It encodes our VC into an SMT query, and whether our program verifies or not depends on the response from the solver. And if we get NSAT, we're happy. But in reality, we often need to make a lot of modifications, as we discussed earlier. That means updated queries, but the solver, even given a semantically equivalent query, could potentially give different responses. And we're no longer happy, and that's the phenomenon of instability or burdenness. Okay, so there seems to be a form of belief that we have to trade off between automation versus stability. On one side, we have high automations. Let's see how these three handle all the undecidable theories. And then, but we get poor stability. So to have more stability, we need to do more manual handholding, so more manual proof steps. And the other extreme is kind of, we just drop down to decidable theories only, and so we lose the automation over quantifiers, for example. But this talk, I would like to cover a bit or have a discussion on can we actually have automation and stability at the same time. So this is drawn from the observation that instability means a mixture of failure and successes. Right. So the high-level idea is that we learn from the successes and we remember the success lessons at the source code level to avoid future failures. And we propose to do this all automatically. So this talk will have three parts. First is detection. That is telling what is unstable. And the second part is debugging. That is to tell why a particular query is unstable. The third part is a bit speculative. It's once we know what's wrong with the query, how do we fix it at the source code level? Okay. I'll go through this very briefly to talk about our work on Mariposa, which is for instability detection. So Mariposa is a tool that takes a query and a solver as a pair of input, and on a very high level answers the question of whether it's stable or not. Okay, the way Mariposa does it is by performing mutations on top of the queries. And the mutations here are meant to be preserving the semantics. That is, say, shuffling the assertions around or renaming the variables. And the intuition here being that if we are seeing certain failures and a mixture of successes coming out of these mutants, then we're seeing instability. So Mariposa, we actually use a series of statistical tests to decide which category query solver pair belongs to. I will not go into the details here, but I would like to just argue for doing these tests a little bit here. Let's just say, for example, we're doing assertion shuffling. Even if we only have 100 assertions, that means we have a huge number of mutants. And we really would like to be statistically sound in the judgment here. But let me not go into too much detail of that. And say that, well, once we we could detect a particular query or label is unstable, can we tell why is it unstable? Let me first talk a little bit about the query context and our work on Shake that discussed the cause of failures in context more generally. So an SMT query is, on a high level, made up of a set of assertions where the overall semantics is whether the conjunction of all these assertions implies a conflict or unsat. So as it turns out, not all of these assertions are strictly necessary towards proving unsat. So as we kind of discussed earlier, a lot of these contexts are irrelevant. But as it turns out, it's a huge amount of context that is irrelevant. Typically, it's more than 96%. And these are from Mariposa benchmark, where we have tens of thousands of queries. And 78% of the instability actually gets mitigated if we were to, say, drop down to the irrelevant context. Of course, that's the idealized case, because sometimes we don't know which are or are not irrelevant. So in Shake, our work at FMCAT24, we had a discussion on how to do SMT level pruning that makes an observation on the context pruning being axiom selection. And we're able to achieve reasonable stability improvement at the SMT level. I would like to talk more today on the specific causes of failures rather than just the general irrelevant context. So that is our work in progress on pinpointing the problematic quantifiers within the query. So again, let's abstract the query as a set of quantifiers. And our debugger, what it does is that given an unstable query solver, it pinpoints particular quantifiers within this query that is responsible for instability. Okay, how do we do that? Again, we come back kind of to the original picture on instability, where we have mutants. Some of them succeed, some of them fail. And the intuition towards answering what's wrong or why is it unstable comes to answering the question of what went wrong in the failed mutant. So in the case of quantifiers, a failure mode includes over-instantiation, or maybe it's under-instantiations. In more details, we could collect the tracing data from the solver, say enable tracing on Z3, which will give us a trace of failure, including all the quantifier instantiations that has been attempted, but doesn't lead to a success, obviously, in this case. And in the case of success, we could ask for a proof of unsatisfiability from, say, Z3. And that would also include quantifier instantiations that are necessary towards constructing this proof. Okay, then the idea is that we kind of differentiate or tell the different contrast these quantifier instantiation profiles to tell what went wrong. Okay, so in more details, our debugger works like this. Start with a query, gather a proof of unsatisfiability, also get a trace of failure. And at the core of our debugger, we have this query editor that performs edit upon the original query based on a single quantifier only. Okay, so we literally try all the each quantifier here and performs one edit on top of it. And each edit is a singleton edit based off just one quantifier. So in more details, let me give an example of what this edit looks like. Let's suppose the phi naught is never used in the proof at all. That means it's probably unnecessary. But at the same time, if we look at the trace, let's say this quantifier is heavily instantiated, then it might be reasonable to suspect that the failure or instability is due to over-instantiation of this quantifier. So within the editor, we could try to remove this quantifier completely, which gives us a new query that is almost identical to the original one, except we don't have this phi naught anymore. Okay, now the idea is that if we rerun stability test on this edited query, now it's stabilized, that tells us, well, our hypothesis on phi naught being over-instantiation is probably right, and that is to be blamed for the failure or instability. Yeah, in a similar fashion, let's say phi1 is needed in the proof, but it's never instantiated in our failure trace. And that it might be reasonable to suspect that the solver is missing key quantifier instantiations of phi1, and which leads to the failure. So what we do in the editor here is we could try to provide the instantiations of phi1 as facts. Right, so just let's say assert them, insert them into the query. So again, if this query is not stabilized, that means V1 is to be blamed. Okay, so that's kind of a simplified picture, but hopefully the high-level idea is here that these edits are meant to reduce or eliminate solvers' need to reason about particular quantifiers. Right, so in practice, we have more edits, but that's the high-level idea. So using this workflow, we have some preliminary results on the Varus benchmark. So in case you're not familiar with Varus, it's a program verification language. A lot of it is inspired by Dafny. So yeah, we have 70 unstable queries from the benchmark. In 4 cases, we cannot build a proof for analysis due to, say, some issues with Z3. But in 62 cases, we can find at least just one stabilizing singleton edit. That is, the instability could be blamed on top of just a single quantifier. And in 4 cases, we didn't find any singleton edit that would fix it. But it doesn't mean that maybe there exists some combination of, say, 2 or 3 quantifiers, and the interactions between them kind of led to the instability. And this is kind of our work in progress on how to intelligently schedule and compose these edits to do better debugging. Okay, so yeah, after we could tell or identify what is wrong with a particular query, the next step is towards repair. This is a bit speculative, but bear with me. Let's say our debugger here reports that the solver has trouble, say, instantiating the quantifier V1. And the intuition here is that we can record and replay the instantiations of V1 at the source level. Right, so the idea is that the solver doesn't need to rediscover the quantifier instantiations every time. Right? It just needs to figure it out once. And we could just record them at the source level. So let me give a kind of a silly example here. Let's say we have an associativity of multiplications as a quantifier, and say our debugger points to this UF lemma, says it's unstable, and it's unstable because the solver has trouble instantiating this quantifier. We could manually adopt to a different programming style in which we explicitly provide the quantifier instantiations, and that would actually fix the problem. What I would like to point out here is that first, these instantiations, we could just ask the solver for them, right? We don't have to manually come up with these. And second, this is a very programmatic transform of the source code, right? So we talked about IDE actions previously. So we already have this framework, proof plumber for Varus code that kind of does these programmatic transform of the Varus source code that would enable such changes. Okay, let me kind of pop back up on our discussion towards automated stability. We have 3 parts: detection, debugging, and the repairing. The takeaways I would kind of like to leave here include that, well, we can enjoy both automation and stability. And the key idea is that we use past successes to prevent future failures. And we can often even localize the cause of instability rather than say it's a general context problem. And furthermore, I would like to root for more statistically sound detection and validation method for instability. And yeah, these are the references. And thank you very much.
Thanks for the talk. We are short in time, so maybe one quick question.
Thank you for the very nice talk. So the slides, that was the title 2.2, gives an impression that to start the debugging process, you need to get the first ansatz, right?
Right.
So basically, if my proof times out and I don't know why, that would not be very helpful. Is that correct?
then it will no longer be a consideration for instability, right? If it completely fails, then it's not unstable, right?
So if it just times out, then, well, there is nothing to begin with, right?
If it times out completely, that is, it never succeeds at all, that's not a problem of instability. It's a problem of, that is not within the scope of the discussion here. We do have some other works on that, yes.
Okay, thanks.
Yeah.
Let's thank the speaker again.